Chapter 12, Section 2, Part 1 begins the gas laws, and the symbols that we're going to be using throughout this chapter are P for pressure, T for temperature, and the unit should be Kelvin. V will stand for volume, and then N will stand for the number of moles. So our first law is called Boyle's Law. This was developed in 1662 by the English scientist Boyle, and his law relates the volume and pressure when temperature of a gas is kept constant. So when temperature is constant, pressure and volume are inversely proportional to one another. So if the pressure increases, then we can decrease the volume. If there is an increase in volume, then we're going to decrease the pressure. So they'll always be opposites. Our equation is P1V1 equals P2V2. So the ones represent the first set of conditions and the twos represent the second set of conditions. So here's a sample problem. If the pressure exerted on a 300 milliliter sample of hydrogen gas at constant temperature is increased from 0.5 to 0.75 atms, what will be the final volume of the sample? So first we need to identify our variables. You can either list them out separately the way I have them written here, or you can at least just identify them right up in the problem and write the symbol above it. So we have our first volume. We have our first pressure, it says it was 0.5 atms, and we have our second pressure, which was 0.75 atms. Now our volume units were in milliliters, so we're going to be solving for our volume in milliliters. If this were in liters, then our answer would be in liters. Now we can also make a kind of an estimate of what this value should be, since we know they're inversely proportional. So since the pressure is increasing, went from 0.5 to 0.75, then that means that our volume has to be decreasing. So we should be looking for a value less than 300. If we don't get something less than 300, we should double check our math. So we're always going to write out our equation first. P1V1 equals P2V2, and then I also showed it rearranged to solve for the unknown variable. You can do this step or not, but you do need to write the equation at least once. And then we're just plugging in our values. So plugging in P1, V1, and dividing it by P2. That will cancel out our pressure units, and our answer is left in milliliters. 200 is in fact less than 300, so we know we at least have a reasonable answer here. And the second law is an English chemist's law. John Dalton, he came up with this law of partial pressures in 1805. And what his law says is that the total pressure in a gas mixture is going to be the sum of the partial pressures of the individual components. So this equation here is just kind of a general equation. Total pressure is equal to the pressure of one gas plus the pressure of the second gas and the third gas and so on, however many gases make up that mixture. So we would actually plug in, N2 for nitrogen gas or H2 for hydrogen gas, whatever the actual symbols would be for those particular gases. So here's a Dalton's law problem. It says a mixture of oxygen, nitrogen, and hydrogen gases exerts a total pressure of 278 kilopascals. If the partial pressures of oxygen and hydrogen are 112 and 101 kilopascals, what would be the partial pressure of the nitrogen? So what we know we've got our total pressure of our gas at 278. We know the pressure of the oxygen. We know the pressure of the hydrogen. We need to find the pressure of the nitrogen. So our equation is going to be P total is equal to the pressure of the oxygen, the pressure of the hydrogen, and the pressure of the nitrogen all added up. So to find the pressure of the nitrogen by itself, we need to subtract the oxygen and hydrogen pressures from our total, and that'll give us 65 kilopascals. Now mole fractions are the number of moles of one component compared with the number of moles in a gas mixture. So this came around after Dalton's time. He didn't know about moles yet at that point in history. And mole fraction is represented by a capital X, and then the moles of the individual component divided by the moles of the total mixture. So to calculate partial pressure, we can use these mole fractions, which mole fractions will stay the same no matter what altitude you're at. So for this one, the partial pressure of A, whatever gas that might be, is going to be equal to the total pressure of the gas mixture times the mole fraction of A. So here's a sample. This one tells us the total pressure of a mixture of gases is 0.97 atms. The mole fraction for nitrogen is 0.78. What's the partial pressure of nitrogen? So we know P total, and we know the mole fraction of nitrogen. So we need to solve for the partial pressure. So writing out the equation, the partial pressure of nitrogen is going to be equal to P total times our mole fraction of nitrogen. When we plug in our values, our 0.97 atms for the P total, and then our mole fraction does not have any units because it would be moles divided by moles. So we multiply those two together and get the individual pressure of nitrogen as 0.76 atms.